So today we're learning Newton's law of gravity, which says then that if we have two objects with the masses m and let's say m capital, and the distance between them is r, they are attracted, and the force of attraction equals g, weight called universal gravitational constant, mass of one object multiplied by mass of another over distance squared. Where g equals 6.67 times 10 negative 11 newtons meters squared per kilogram squared. As this value is very, very, very small number. So gravity is a very, very big force. And to be gravity to be not very small, we need to have huge mass involved. Because, for example, there is a non-zero force of gravity, force of attraction between any two objects that have mass. For example, there is a force of attraction, non-zero force of attraction between Eli and Neo, for example. But if we calculate how big is this force, we will have 6.67 times 10 negative 11 times, we will estimate those methods, let's say 70 times 90.
I'd say it would be more
distance, let's say 1 meter or 1 over 1 squared. So if we calculate that will be 6.3 times 10 to the power of 4. So we will have approximately, about 4.2 times 10 in negative 8. Can you please sound check with the calculator?
-7.
And the number?
4.2.
4.2 times 10 negative 7. So force is so small that we cannot feel it. But as soon as object with a big mass like Earth is involved, we feel it. You really feel it. If you jump, don't try, then of course your force of gravity immediately pull you down.
Does that mean that the biggest person in the class, everyone gets pulled towards him?
But then, according to Newton's law, that person gets pulled towards every one person.
That's why you're right.
Now, from here, yes.
But does if you're, let's say we're on Earth, so that's way bigger, more gravity, does that lessen the force between, let's say, me and Joseph? And if me and Joseph were in space, so Earth would be more attractive than if it was...
No, it doesn't matter. Force of attraction between you doesn't depend if the third object is involved.
Right, so even if something's pulling us, like the Earth is pulling us way more, it doesn't change how much...
You attract to each other. Yes?
Since the formula is m over distance squared, if the distance was really small between me and the table, would it attract higher?
What do you mean really small?
Like if it was like 0.00001 meters away.
So how close you can think you can get to the table?
Very close.
Very
to the
close.
center of mass.
Very close in meters. What is very close in meters?
I don't know.
Let's say if you get to if you get close 1 micrometer, 10 negative 6.
Okay.
10 negative 6. It still will be pretty small.
No, that squared is pretty large. That's
10 negative 12
will be...
Okay, no, you probably will not get to 1
It
micrometer.
gets like half a millimeter.
Let's say you get 10 negative 4. It still will be 10 negative 3 newtons. It still will be very small. Now, we can now...
Doesn't make sense. If I can touch it, that means I can go very small.
If you touch it,
Yeah.
where is your center of mass? Because we're talking about the distance between center of mass.
Okay, so
Your
if I lie on the table.
center of mass, usually it's with some somewhere
if I
there.
Yeah, Joseph, that's not at least like
Just-
Joseph, you didn't have to spoil
Still,
it.
you will have some distance.
Oh, because from my center and the table is still
Yes,
like
it's
my
still-
stomach. Right?
Yeah. Okay, now we can give the new, now we can give a new sense to G. How we were calculating the force of gravity before? Which formula we were using?
Acceleration.
MG.
mg.
Back.
And they're the same force, so we have mg equal gmm over r squared. Mass cancels out and we get for g m on r squared, where r will be in this case radius of Earth, mass of Earth. And through this part we will call g now not acceleration due to the gravity, we will call it the gravitational field strength. And unit we will be using, and still you can use kilogram meter per second squared, but it's the same from here, it is Newton per kilogram, which is the same thing. Gravitational field strength. G is gravitational field strength. From here we can see that the G depends on this is on the surface of the Earth. If you're going higher, we need to calculate distance from the center, and the G will be decreasing. G will be decreasing as higher we are going. So, what mathematically is this relation? This is R, this is G, this is surface of Earth, so we have on surface of Earth 9.81. What mathematical relation is that?
hyperbola.
Truncus.
Oh, trunk.
Exactly.
So I was thinking of trunk.
So
we
that's
forgot
how
what that
it
is.
will go. So the higher we are, the less G. What will happen if we drill the hole
Negative.
through the Earth and we will go inside?
Well, it swaps.
Really
Yeah,
hard.
Now what happens to the G?
It gets stronger.
Really, really strong. Really weak.
Wait, what do you mean drill it?
It's a hyperbola. You have to
We
draw the-
drill through the Earth, take your big drill
Yeah.
and drill through the Earth.
And split it into.
China.
Not split it, not cut it too.
So what do you
Drill,
drill?
a hole in the earth
drill a
and
hole,
drop it.
drill a hole like that big so you can fit into that hole,
The center.
and you jump into that
The
hole.
center of the
Yes,
center
all
of
through.
Through the sand, completely
Like a
through the
straw.
whole Earth. Through the Earth. From
Then-
one end to another. From Australia,
Well, if
and
you
what
drill a
will
hole
be,
through the
and
earth,
you
it's
get
the
out
earth
somewhere
walls,
in
it's just
America.
smaller.
No, okay, just like a straw. It's not cutting it in half.
Not cut in
Oh,
half.
yeah, true.
The small.
Wouldn't it oscillate but get smaller? and then
No,
bring it
what will happen with G while we're going
Oh, so
inside?
it's increase.
Smaller.
Going towards the center.
It'll be smaller, obviously.
Bigger, because it's underneath.
No, because radius
Actually
decreases.
stupid.
Radius decreases.
Bigger.
Getting in the center, it will be zero.
Oh.
In the center of
Yeah, that
Earth,
makes
G equals zero. Why? Why it will be zero?
Because you're getting pulled to the point that you're already at.
Because you will have same mass to the right of you, to the left of you. Same mass above you, below you, in front, behind. So you're pulled evenly in all directions.
Wait, so that means, Mr. V, if we were here
Oh, bigger.
and there was a hollow hole through Earth and I jumped in, what would happen? Would I just float?
No, the thing is you will get, because you will get some velocity here, you will get through, then you get, and you will be like oscillating up and down.
Ah, is that what we're doing at Luna Park? We're jumping.
Yes.
But wouldn't it get higher and higher as it approaches the center point, and then when it gets to the center, it'll be zero?
No, it becomes smaller because when we're getting inside, let's say, we get here,
Becoming more and more balanced.
we get here, and we will have,
G decreases but velocity.
You have net force
if we
going
draw
into the
like this, we will have this will pull down,
It's resolving the forces.
this will pull, this beat will pull up.
It makes sense.
And this will be bigger, so it's not 0 yet, but it will be smaller because as more we go in, we'll have more and more mass pulling us.
Mr. Does that also mean if you go at rest into the center of the Earth, you're just going to float?
Yeah. Yes.
Really?
Yes.
But then at what point on the surface of the Earth does it start getting weaker instead of getting stronger? Because if you're going further away, if you're going from the centre, further away towards the surface,
Yeah. When we get to the surface, it's on the surface 9.81.
but then the surface, okay, if you're on like the highest mountain and the lowest mountain,
Okay,
it's different.
let's calculate what will be the G if we, let's say, get the radius of Earth approximately, it's I think 5.37 times 10 in the power of 6 meters. That's what on the formula sheet, I think. Someone have formula sheet with him?
Probably.
No,
If you check, I think it's 5.37. No, it's not 5.3, it's 6.3. Sorry, 6.37. 6.37.
6.37 times 10 to the 6.
6, yeah, 6.37 times 10 to the
What's
power.
the mass of Earth?
We don't need it.
The mass of Earth
Because-
is 5.97 times 10 to the 24.
Let's write it. Can you repeat it, please?
5.97 times 10 to the 24.
Times 10 to the power 20. Let's calculate if we go above the Earth to the distance equal radius of the Earth. So this is radius of the Earth, and we go another radius of the Earth up. So we have on the Earth, we have G equal, we have G mass of the Earth over RE squared. G2 at
G,
the height we will have GME divided by 2 radius of Earth squared, which is 4. Let's divide second equation by the first.
1 on 4.
We get G on 2 over G of 1 will be equal
I need to go
to
back
1
to math.
quarter. So if we go
Never mind.
that high above Earth,
G2 and G1.
G will decrease 4 times.
Yeah.
When G and GM cancels
But
out,
Mr. V,
yeah.
if you go in the Earth a little bit, G will also decrease relative to when you're on the Earth.
Yeah, it will be decreasing. That's what graph will show you.
Yeah.
If you go in, it will
So
be
it's the
decreasing.
strongest on the Earth. Like it's the
On the
strongest.
surface,
Where
yes.
Yeah.
But the surface isn't flat, so where is the strongest? Is the strongest in the bottom of the valley or at the top of the mountain, or is it in the
Well,
middle?
we're
Where
taking it
is
as a perfect circle.
Yes, we approximated. Where it will be the strongest,
wherever they measured the radius from.
probably I will say on the like some on the flat.
Yeah, how did they
It will become lower when you go in some deep. It will become lower when you go into the mountain. Becomes lower. So does that make sense that the gravity acceleration due to the gravity becomes 4 times smaller when you go in 1 radius above the Earth? Make sense?
Is that leaving the atmosphere if you go radius above the Earth?
Will be the atmosphere? No, there will be no atmosphere because that is in kilometers. That is about 5,970 kilometers. Atmosphere is about up to 100 kilometers. So there will be no atmosphere there.
So gravity
Am I in
still works
space?
when you're outside, when you're in space?
Hmm?
Gravity, when you're in space, is still attracted to
Yeah,
Earth.
of
when
course.
You're, yeah.
You're still attracted,
That's
and
Or less.
you're attracted. Like Earth is 150 million kilometers from the Sun, but it's still attracted to the Sun.
Yeah.
Well, because the sun.
Gravity acts over distance. Now, the gravity is the biggest of all known forces. We will see when we will start learning about other forces, you will see how much stronger is, let's say, electrical force. And it's an interesting question why gravity is relatively so much weaker than other forces. And one of the ideas is that gravity might be spread more than in 3 dimensions. That's some ideas why gravity is so weak. compared to
Well, how
other
does
forces.
Four-dimensional gravity.
Hmm?
do we have to learn how gravity works?
How it works? No.
What's the other dimension?
Well, can you like easily
Time.
explain why it works?
I don't actually know.
Can you easily like briefly explain why gravity works?
Why gravity works? Everything that has mass. Now, very good question. First of all, we say there is you need to be touching Earth to be attracted to it? No. So gravity acts over the distance. And we say when some object acts on another object over the distance, you say that there is a field created. There is a field created. And when there is a field, there is an exchange of the force carriers. And for mass, for gravity, there is a such thing that gives every particle its mass. It's called Higgs boson. It's called Higgs boson, which was predicted in 1960s and discovered in 2011 in the Large Hadron Collider. Interestingly, it took 50 years to actually catch that particle, which was theoretically predicted. But that's all well beyond the school curriculum.
Wait, so what's this Higgs boson? What's the point of it?
Higgs boson is a particle that gives other particles their mass. We're not going into this, it's not part of the school, it's well beyond the school curriculum. We can, at some stage, we have time, we can look into it a bit, but let's keep things simple. So, if we, let's say, this is a massive object, if you place another object here, in which direction force will be acting?
Center.
To the center. So we can visualize the field by the drawing field lines. Field lines which gives us direction of the force acting if you place an object in that point of field. So that is visual representation of the gravitational field. And as closer lines are, those called lines of the field, the closer lines are, the stronger is field. When you're going away, lines becomes further away from each other, the field obviously weaker. And this for gravitational field always non-uniform. What does it mean uniform? Same everywhere. So gravity always non-uniform. So it's we change distance, we go into another place, will be different force.
Is it only non-uniform because if you have something that the gravity is acting on, it changes it, or is it like if
No, because of the shape, we cannot make gravitational field to be its uniform. And important thing, there are things called monopoles and dipoles. Gravitational field always monopole, it's one pole, because with gravity, at least to our current knowledge, there is only attraction. Gravity is always attraction. We'll learn later on, we'll see that electrical field can be monopole, can be dipole, and magnetic field only dipole. You cannot have magnet with one pole. With electric field, we can have either separate positive, separate negative, or bind it together. But that's later on.
You said it is uniform?
No, this is non-uniform. Uniform field, let's say electric field, jumping a little bit ahead, between two metal charged plates can be made uniform. So it's same at every point. That is uniform field.
Right.
But you cannot do that with gravity. Gravity is non-uniform field. So that is the Newton's law of gravity. When you will be solving problems, very important, and do calculations, very important thing how to do calculation, because it is super easy to make a silly mistake when you're dealing with a huge force, with a big masses, big distances. It is very easy to make a mistake. For example, open your booklets on the page Open your booklets on the page 108. 108. Question 1b. Find the gravitational force of attraction between the Earth and the Sun. Numbers here are slightly different and more rounded compared to what you have on the formula sheet, but we will be using those numbers. We will be using those numbers. So, F equal G, mass of Earth times mass of Sun over radius of the Earth orbit squared is 6.67 times 10 negative 11 times mass of Earth, here rounded to 6 times 10 in the power 24, mass of the Sun 2 times 10 in the power of 30, divided by radius of the Earth orbit 1.5 times 10 in the power 11 squared. And you don't have your case calculators, unfortunately, on the physics exam. So you need to use scientific calculator. And if you will put all of that in the scientific calculator, you will be unable to see the whole expression on the screen. And it's so easy, you type one digit wrong, and you stop it. So, do calculations in two parts. It will take extra 30 seconds, but prevents silly mistake. If you split it, calculating numbers, 6.67 times 6 times 2 of 1.5 squared, times, and you do power separately, 10 negative 11, 10 in the power 24 times 10 in the power of 30 over 10 in the power 22. If you do
3.56. 3.56.
3.56 and the power we have 54 minus 22, 32 minus 11, 10, 23.
To the 22, because it's 35.6.
35. So if you calculate, you will get 35.6 times 10 in the power 22, which you, no.
3.56 times 10 to 22.
So first, when you calculate this, you get 35.6, right?
Yeah.
That's what you will get.
Yeah. So
Times 10 in the, again, we have, that will be 13, 13, 40, 43, 21 will be 10, 21.
Yes, then 22.
That equals 3.56 times 10 in the power 22 newtons. Spend this extra 30 seconds and will be less chance to make silly mistake. Split it into calculations. Numbers separately, powers separately. Make sense?
Mm-hmm.
Yeah.
And one more question that I want to show you, question number 8 on the page 109. At what distance from Earth would a spacecraft experience zero net gravitational force due to the opposing poles of the Moon and Earth? So we have Moon, we have Earth, we have Moon. And we have this some point where, because Earth will be pulling it in one direction, Moon pulling in the opposite direction. And there will be some point where overall force will be zero, because those forces will be equal. Let's take, because it's asking to find the distance from Earth, so let's take this as x. And this distance is radius of the Moon's orbit. Moon orbit. So if this distance is x, what will be this distance? We'll have r minus x. And then we equalize the forces. We have g, m of the spacecraft, times mass of the Earth over x squared, equal G M mass of the moon over R minus X squared. That is, we have two forces in the opposite directions and they are equal.
So G and M.
Now, G and M cancels out. And the best way to do it, what will be the best way to do it? How will we write it?
Drag formula.
Hmm?
Drag formula.
That is the most difficult way to do it. So if you write it as R minus X squared over X squared will be equal M of the moon over mass of the earth. And then R minus X divided by X will be equal square root of mass of the M or mass of the earth. So R on X minus 1 equal square root of mass of moon over mass of earth. So we get R on X equals 1 plus square root mass of the mass of the earth, and then you can find the X. That's the easiest way. Quadratic, you can use quadratic formula. Believe me, it will be much harder calculations. Yeah, do use the calculators and calculate what will be the distance.
So what actually is big G? Like, I know
Big
it's a
G?
constant, but what actually is it?
I will explain it in a minute. Let's have do calculate this calculation. And an excellent question.
How do they even find it? You can go with that.
So you from here you will get X will be equal R divided by 1 plus equals 1 over 1 plus square root of mass of Earth divided by mass of the Moon. Sorry, R. And that will be equal.
Mass of the
R of 1.1
X is equal to
R of 1.2,
times.
which is then
Yeah. Have you got it?
No, I was typing it out of the bracket and I accidentally clicked clear. So I just started doing that.
would it happen to be 3, 4, 5, 7, 5, 7, 6, 7, 9.3?
No, I got 3.8 times 10 to the.
No, 3.5, rounding, 3.5 times 10 in the power of 8.
James, I think it was just a calculation.
Yes, I would agree.
Yeah,
You
so
rounded.
you did something wrong.
No, I think it's
Why?
supposed to be maybe just rounded.
Yeah, but which way?
3.8, 3.5, no.
Do you want
Something
else
wrong.
to calculate?
Well, have a look, have a look. So I started. Yes.
Yeah.
Divided by.
Just I think it's hard to make resets before coming in because coming in here you lost.
That.
Why is that we did? No, it's maybe.
Yeah, then you probably wrong.
I didn't.
Okay, now, for the excellent question, what is the meaning of the big G? Gravitational field
I
strength.
didn't square root of this.
On
I didn't do, haven't done square root yet, that's why. So,
So it's 1.
I will rewrite and the law of gravity, F equal G M M over R squared. When F will be equal G?
when M and on R
M
equals
was
1.
So, when we take mass equal each of object 1 kilogram
And radius equals 1.
and distance is 1 meter, we will get F equal G. So G gives us the force with which two 1 kilogram masses will be attracted at the distance of
Well, that's
1
not
meter.
necessarily the only case.
What if m equals to 1,000?
The G is the force with which two 1 kilogram masses attracted at distance 1 meter.
Wait, why can it not be a radius of 2 meters or both?
But
No.
yeah, of course you can change the proportion. If we increase one mass twice to have the same force, what should be happens with that?
Increased by root 2.
Like,
We make one of the masses twice bigger. To have the same force, what we need to do with that?
Increase the radius.
Make a root 2.
Yeah.
Increase by factor of root 2.
Oh, really? Just say that.
Increase by the factor of root 2. Make sense?
Yeah. Isn't that like Confucius laws or something?
No,
Oh,
nothing but Confucius.
Okay, that's all explanations for today. Like, subscribe and donate, and now pretty much everyone needs to help Ukraine after America betrayed it and signed it with Russia, and now pretty much it makes the whole world in danger.